Okay, hi everyone. This is going to be a video about the matrix equation AX equals B. So if you've been keeping track with the lessons up until this point, I guess we could say that in the last lesson we had vector equations. We talked a lot about vectors, we talked a lot about Rn, and we introduced some concepts like linear combination and span. So this section is going to build on those topics, so it's important that you know what those definitions were. Okay, so let's go ahead and see what we can do. So the matrix equation AX equals B. I'd like you to notice which ones have the vector symbol above them. It's the X and the B. So X and B are vectors. A does not have anything, like there's no symbol above the A. We often use the letter capital A to represent a matrix. Here, let's go ahead and get started. Definition. We are going to let capital A be a matrix made up of these columns. Remember last time we said that it's possible to write a matrix in this format. It's comprised of these column vectors. We're going to let A equal that. We're going to say that A1, A2, ... up to AN are all elements of Rm. Notice that that's an M, not an N. Okay. And let X equal the column vector X1 ... down to Xn, which is an element of Rn, period. We haven't really gotten to the definition. This says definition. All I have so far is we've established that A is a matrix made up of column vectors. There are n columns. Each one of them lives in Rm. So each column then means each column has m entries. Just that first part. What is that saying about this matrix A? It has n columns, and each one of them has m entries. So I guess we could say that A is m by n, if we were talking about the size of the matrix. M rows and n columns. And then X is just a column vector with n entries, so it lives in Rn. So what's the definition going to be? The product of A and X. We haven't done this before. In this class, we have not had the product of a matrix times another matrix. We had, I guess in the previous lesson, we may have talked a little bit about adding two matrices together, subtracting two matrices. We even did what was called scalar multiplication, where you have a scalar, or a real number, times a matrix. But now we're talking about a matrix times a vector. That's new for us. And that's going to be denoted simply AX. And we are going to say that it is AX equals. So first of all, here's A. Second of all, here's X. Notice that each of the things that I wrote in A is a vector, so each of these are a column vector. So A could be a rectangular matrix, but X is just a single column. So what is it going to equal? Well, it needs to involve these X's and A's in some way. It's actually going to equal the first entry of X times the first column of A plus the next entry of X times the next column of A plus the next entry of X times the next column of A, etc., until we get all the way to the last entry of x times the last column of A. Notice that it worked out perfectly because we had n columns in A, and we had n entries in X. So when I wanted to go from the first one to the second one, the third one, when I wanted to get all the way to the last one, we have the same number of things to match up. I'm going to say underneath that we must have that. The sizes must match up. We must have the number of columns in A equals the number of entries in X. And if we're following this definition, then we do have that, because look at A. A was defined to have n columns. And then look at X. X was defined to have n entries. So it all works out. I'm just going to say otherwise. Otherwise, the product AX is not defined. So, there is our definition. Let's do an actual example of this. I've got a couple of these. I think I'll do one, and then I'll have you try one. But let's do some examples with some specific numbers in here, and we'll be able to see A as an actual rectangular matrix. So we are going to say evaluate and simplify, and I'll talk us through this first one. We are going to be given a matrix times a vector. So here is our matrix. Here is our vector, 4, 5, 2. And I'm going to follow the definition above, and I'm going to show you that we can get the answer. All right, so what does it say to do up here? It says take the first entry of the column vector. So we're thinking of this as A and this as X. Take the first entry of X, in this case 4, times the first column of A. Add that to the next entry of X times the next column of A. Add that to the next entry of X times the next column of A. If the sizes line up, then we will find that we are done. There were 3 things in X, and there were 3 columns in A. This problem says to simplify. So what should we do to simplify this? I guess we have little scalar multiplications to do, don't we? We have like 4 times a vector, 5 times a vector, 2 times a vector. Let's do those. So 4 times this first vector gives us 4, 8, negative 4. 5 times this vector gets me 15, 0, 10. And 2 times this last vector gets me 8, negative 2, 6. So is that the final answer? No, we could simplify this more. We can simplify this more. Because right now what we have, the last part that we wrote, is a vector plus a vector plus a vector. Well, why don't we just add them together and merge them all into one? Here, watch this. I'm going to merge them into one vector. How do I do that? You add the corresponding entries. 4 plus 15 plus 8. This is going to be 8 plus 0 minus 2 minus 4 plus 10. We're kind of squishing these numbers in here. So let's write the final answer over here. The final answer is going to be where I evaluate those. 4 plus 15 plus 8 gets me 27. 8 plus 0 minus 2 gets me 6. Minus 4 plus 10 plus 6 is 12. And that is going to be the final answer. So we started with a matrix times a vector, and the answer is a vector. And all we have to do is a bunch of adding and multiplying. So let me give you one like this to try. See, it looks complicated when we say the definition, but when we actually do it, it's not that bad. I'm going to ask you to try a problem of the same size. Okay, so this would be a good spot to pause the video, take a minute, and see if you can do this one. Evaluate and simplify. All right, if you tried that, you should get 6 times the first column plus 0 times the next column plus -2 times the last column, 5, 1, -4. Hey, look at that. We've got a 0. 0 times the second column. 0 times something is just 0. We can cross that out. So that's really nice. That's going to make this easier. In fact, I think we could say that anytime there's a 0 in this vector, it's going to kind of save us some work. Okay? So this is going to be 12, 24, 18. I'm going to say plus, but let's be careful about signs here. If I say plus, then we have -2 times 5 is -10. -2 times 1 is -2. -2 times -4, +8. Add this up, and you should get 2, 22, 26. And that is the only answer to this problem. Okay, so we're able to do a matrix times a vector. And we're thinking of it as a matrix A times a vector X. Now, the name of this section was the equation AX equals B, and so far we've been doing the left-hand side of it. We've been doing the AX part. So now we need to talk about the rest of it. What about the equals B? So this is going to now be the equation AX equals B. And we know how to do the left-hand side. Often, in math, we often have equations and we want to solve for something. So you might say, if we have this kind of equation, what are we going to be solving for? Well, you'll see. We'll get there. All right, consider the system. We're going back to linear systems. x1 minus x2 plus 3x3 equals 4. Actually, I think this might be one that we've seen before. Sometimes I reuse systems across multiple sections just to have something familiar and be able to illustrate lots of things about the same system. All right, so maybe we might have seen this before. So this is a linear system. And I want to say that we could think of this equation, this is a system of equations. We could think of it as vectors. What if I wrote a vector on the left equals a vector on the right? The right-hand side being 4, 10, 14. And the left-hand side being x1 minus x2 plus 3x3, x1 plus 2x2 minus 2x3, 3x1 minus x2 plus 5x3. Now, I want to be clear about something. The left-hand side that I just wrote is a column vector. Okay? It looks like rectangular. It looks like it's wide. The only reason it looks wide is because I wanted to fit this long expression in there. But there are 3 entries here. Top entry is x1 minus x2 plus x3, 3x3, right? That is one thing. Maybe it'll help if I circle them. Like, there are 3 things in this vector. That's it. It's not like a 3 by 3 matrix or anything like that. It's a 3 by 1 matrix. There's 1 column. The right-hand side is also a 3 by 1 matrix. There's 1 column. And when I write it this way, notice that I only need 1 equal sign. We only need to write 1 equal sign here because I'm saying this vector is equal to this vector. Okay, so far? This is equivalent to, watch this, x1, 113, plus x2, -1, 2, -1, plus x3, 3, -2, 5, equals 4, 10, 14. So it's kind of like I've done the opposite of what we were doing in those previous problems. In the previous problems, we had something like scalar times a vector plus a scalar times a vector plus a scalar times a vector, and we merged everything together to simplify it. Well, now I have one vector, and I'm splitting it apart into scalar times vector, scalar times vector, scalar times vector. So we took one vector, split it across into this whole thing. Furthermore, this is equivalent to, according to what we said earlier about the definition of the product of A times X, we could write a matrix 1, -1, 3, 1, 2, -2, 3, -1, 5 times, here, let me write some of this. What do you think needs to go in this missing vector here that I wrote in the middle in order to make this line equivalent to what I have above? It's going to have to be x1, x2, x3. So we've done a few things here. We started with a system of linear equations, just like we did in the first lesson of the semester, where we're like interested in solving systems of equations. And I'm saying that we can sort of correspondingly think of it as just a vector equals a vector. And then you could take the left-hand vector and split it up into this whole thing. And then you can use the definition from the beginning of this lesson to say that this is equal to a matrix times a vector. And if we'd like to, we could call this A. We could call this X with the little vector symbol. And we could call this B with the little vector symbol above it. So we had a system of linear equations, and we found that it is equivalent to this other equation that involves a matrix and 2 vectors. There's nothing particularly special about that system. In fact, it seems like maybe you could do this with every system. So here's a key idea. Key idea. Any linear system can be rewritten as AX equals B, where A is we have a name for A. We're going to call it a coefficient matrix. comma, x is a vector of all of the variables. Those are usually the unknowns that we're solving for, right? And b is the right-hand side. A vector made up of the entries from the right-hand side. So this coefficient matrix is not to be confused with the augmented matrix of the system. The augmented matrix of the system would include the right-hand side, but this coefficient matrix does not. So this is a big deal because this is basically saying, you know, in linear algebra, some of the things that we like to work with are systems of equations, matrices, vectors, and some other stuff that we haven't gotten to yet. But this is saying that systems of linear equations can be thought of in terms of matrices and vectors, and also vice versa. Matrices and vectors can be thought of in terms of a linear system. So we have a theorem to kind of formalize this, and this is called Theorem 3. And it says, let A be m by n with columns A1, A2, up to AN, and let B be a vector from Rm, make sure that's an M, and let X be a vector from Rn. By the way, I guess we didn't really specifically say this, but it's kind of implied that M and N are positive integers. And they could be equal to each other, but they don't have to be. You know, you could have a 3 by 3 matrix, or you could have a different size. 3 by 4, 4 by 3, whatever. Then, the matrix equation AX equals B has the same solution set as the vector equation. Here, let me move some things up here. The vector equation x1a1 plus x2a2 plus dot 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 plus xn an, all of that equals b, comma. We have more to say here. Let me just give you a chance to see all that. Which has the same solution set as the linear system whose augmented matrix is. Augmented matrix needs to have everything that the coefficient matrix has, and it also needs the last column to be the right-hand side, period. That's the end of this theorem. The theorem is basically saying what we have said above. It's just making it more formal. We kind of did it above with one specific example, so that's not really a full proof of this theorem, but maybe the example that we did convinces you that this all seems plausible, that this should work for any linear system. I want to follow this theorem with a fact, and this fact, I think, could be viewed as a corollary. Sometimes we say corollary in math when we have a fact that follows immediately from a theorem. This one is just labeled fact in the book that I'm looking at, but it could be called a corollary. It says AX equals B has a solution if and only if B is, before I finish the sentence, let me just show you what I'm getting at. In order for this system to have a solution, there would have to be an x1, an x2, an x3, all the way up to xn. There would have to be those numbers that make this thing true. If this thing is true, then B is a linear combination of the columns of A. So linear combination was a definition from last time. But we're seeing it show up here because we're looking at this vector equation here, and it kind of looks almost like the definition of linear combination. B is a linear combination of A1, A2, A3, etc., with weights x1, x2, x3, etc. In other words, what's another way we can say this? In other words, B is in the span of A1, A2, all the way up to AN. Because remember, what does span mean? Span means the set of all linear combinations of those column vectors. So if B is a linear combination of those columns, then it is in this set. So we're kind of connecting a lot of concepts here. We're connecting the concept of linear system that we want to solve. We're connecting this with the idea of matrices and vectors. We're connecting it with the idea of a linear combination, and also using the concept of span. Maybe we're saying that there are lots of different ways to view a linear system having a solution. Now, recall if some vectors, v1, v2, up to vn are in Rm, if these are in there, we say span of those vectors is the set of all linear combinations of v1 through vn. Notice that the span of a set of vectors like this it's a set of vectors, right? Some vectors are in this set. Some vectors might not be in this set. I want to say notice that it is a subset of Rm. How do I know that? It's because all of the V's are in Rm. So if I take a linear combination of the V's, I'm also going to get something that's in Rm. We're not going to do a linear combination and then all of a sudden it has like a taller column. It's not going to change size. So if it was in Rm, you do a linear combination of them, you get something that's also in Rm. That brings us to a question. Can we have the span of a set of a bunch of vectors? Can we have it actually equal Rm? We know it's a subset of, but can it actually equal the entire thing? And if so, what would it mean? Well, I guess this would mean that every vector in Rm, every vector you could think of, can be written as a linear combination of the v's. So you pick any vector you want with m entries, guaranteed that it can be written as a linear combination of these v's. Would the v's have to be kind of special to make that happen? Would there have to be a lot of them? A lot of these v's in order to make that happen? All right, well, the answer to this is yes. We can have that. It is possible. And in this case, we say that the vectors v1 through vn span Rm. I'm going to underline that. I'm using this as a verb. So we're using the word span a little bit differently now. So far we've talked about the span of, like the span of a set of vectors. And I think last time we also said the phrase spanned by. But now I'm using just the word span as a verb. These vectors span Rm. Now, how can we tell? If we have some vectors, how can we tell whether or not those vectors span Rm? I might refer to Rm as the space that these vectors live in. How can we show that these vectors span the entire space? I'm going to show you. I'm going to show you an example. I claim that the span of these two vectors, only two are needed. I claim that that equals R2. And I am going to prove this to you. I just want you to make sure we understand what we're trying to prove here. We're saying that, so the span of these two vectors, it's every linear combination of these two vectors. So what does a linear combination of these two vectors look like? It would be a constant times the first one plus a constant times the second one. I'm saying that when we set things up in that form, we can get all of R2. We can get any vector with two entries as a linear combination of these two things. We're not missing any vectors at all. Now, to prove that, the left-hand side is a set of all vectors of this property. The right-hand side is also a set. It's a set of all vectors that have two entries. So to prove, how do you prove that two sets are equal to each other? You've done this before in the previous class. You need to show that the left-hand set is a subset of the right one, and the right-hand set is a subset of the left one. You need to show both directions. Okay? Now, a lot of times when you're doing those kinds of proofs, a lot of times one of the directions is easier than the other one, or you might even say one of the directions is sometimes just kind of follows from definitions. So I'm going to say that this is true by definition of span. I think we can see that everything in the left-hand side must be contained in the right-hand side, because when you do, a scalar times this plus a scalar times this, you're going to get something in R2. There's not much more to say about that. We want to show the other direction. And that's kind of the more interesting one. We want to show that R2 is a subset of this. How do you show that R2 is a subset of this? Well, pick an arbitrary element of R2. So let's pick an arbitrary vector of 2 entries. I'm going to call it x1, x2. It lives in R2. I want to show that this is in the span of those 2 vectors. So what does it mean to show that this is in the span of that? It means that we want to find weights C1 and C2 so that C1 plus 2, 0, plus C2, 1, 3. All right, we want to show that this is possible. We want to show that there is a C1 and there is a C2 that makes this a true statement. By Theorem 3, this is equivalent to solving the linear system with augmented matrix to 1, x1, 0, 3, x2. We're still in the middle of this proof. We've just gotten to something that looks a little different from what we're used to, because I think we're used to having a system where x1 and x2 are the things we're trying to solve for. But now we realize in this context, we're not really trying to solve for x1 and x2. We're trying to find c1 and c2. If we can show that there is a c1 and a c2 that exist that make this work, then we'll be done. Can we even solve a system like this? It has a weird right-hand side. All right, let's try it. I'm going to say we have, and let's work on this augmented matrix. 2, 1, x1, 0, 3, x2. I guess you could say it's in triangular form already. That's nice. It's in, it's in row echelon form, but we could try to get it into reduced row echelon form because that would give us the solutions. So I'm going to do some row operations on this. Yeah, let's try to do row operations, get some 1s as the leading entries, with the 0s above and below. So if I want to get the leading entries to be 1s, then I don't really like having a 3 here. I would like this 3 to be a 1. So what I'm going to do is row 2 times 1/3. I'm not changing anything about row 1 right now, so just copy it. That gets me a 1 here. And it also changes this thing. It changes this to x2 over 3. Okay, that's fine. Next thing, we're trying to do, Gauss-Jordan elimination, get this into reduced row echelon form. So what would be a good step here? How about we try to get rid of this 1 that's up here? We've got a 1 in the first row that we'd like this 1 to be a 0. We could do that by subtracting row 2 from row 1. Like add negative R2 to R1. So we'll have a 2 here. We'll have a 0 here. That's what we wanted. By the way, we're not changing row 2 in this step, so I'll just copy row 2. All right, what happens to that other entry? It was x1, and it needs to have something subtracted from it. It's now going to be x1 minus x2 over 3. Okay. I think we're one step away from having this in reduced row echelon form. Reduced row echelon form says that the pivots, the leading entries, need to be ones. And then there need to be nothing but zeros above and below them. There's a 2 here. I don't like that 2, so I'm going to multiply that row by 1/2. So R1 is getting multiplied by 1/2. So we get a 1 here, a 0 here, 0 here, 1 here. Look, this is working out great. So this is x2 over 3, and we have to figure out what's this new upper right entry. We multiply what we had by 1/2, so x1 over 2 minus x2 over 6, period. We solved, did we solve the system? Did we find C1 and C2? Well, remember that x1 and x2 were just left as unknowns, right? This is an arbitrary vector in R2. So if we were going to try to find C1 and C2, the best that we could hope for is to find C1 in terms of x1 and x2, and to find C2 in terms of x1 and x2. So we did that. I'm going to say let C1 equal what we found. It's a 6 down there. And let C2 equal what we found for C2. And I'm going to say that these values of C1 and C2 exist for any x1, x2 in R2. And they yield x1, x2 being in the span of these two vectors, which ultimately that's what we were trying to show. We started with an arbitrary vector in R2. We showed that it is possible to write it as a linear combination. We had to find the weights, C1 and C2. We found the appropriate weights. These weights do exist for any x1 and x2. Because looking at them, no matter what x1 is, and no matter what x2 is, like pick any real number for x1, any real number for x2, these expressions always exist. Now, maybe we'd have a different story if there was like an x1 in a denominator, and then you could get kind of picky and you could say, wait a second, what if we have a 0 in the denominator? Then this all falls apart. But we don't have any problems like that. The denominators are 2, 6, 3. x1 and x2 can be any real number, and these fractions will always exist. Okay, let's just finish this up by saying, therefore, we had an arbitrary thing from the R2. We showed that it is an element of this set. Therefore, we showed that span of this it's a 1 and a 3. This equals R2. And that's the end of the proof. I'm going to put a little square here to indicate the end of the proof. So, what do you think? Do you think there's something special about these two vectors, 2, 0 and 1, 3? Do you think I set this up because those two vectors are special and that they kind of generate R2? No, not really. There are other pairs of vectors that also span R2. This is just one example of a pair of vectors. I'm using the word pair. What if I had what if I had 3 vectors in this set? Could that also span R2? Yeah, it could. I guess the problem that you're solving here would be a little bit bigger. Okay, I'm getting ahead of myself. Let me tell you a fact. Fact, the span of this and this also equals R2. I'm going to move the page for just a second to show you something, okay? Up here at the top of the page, I claimed that the span of these two vectors equals R2. We went through this work to prove it, and it is a true statement that the span of these two vectors is R2. Now, at the bottom, I'm saying a different fact. Span of these two vectors equals R2. We could prove this in a similar way. And for the proof of this, I'm going to say, try at home. Try that on your own time. That would be good to do for practice. You could do a similar strategy to what we did up here. It might work out even nicer because you don't have like the 2s and 3s to worry about. So what we're saying then is that the set of vectors, maybe I'll write what I'm saying here. All right, so the set of vectors whose span equals R2 is not unique. We could say that the span of, here's a couple of vectors, the span of them equals R2. Here's a couple of vectors, the span of them equals R2. All right. Do you think that, here's a question, do you think that I could just pick any two vectors? Would that work? Like if I said span of, pick any two vectors that you could think of here. I don't know, 1, 2, 3, 4, something like that. Would that work? What about 1, 1, 1, 1? Would that work? What about 0, 0, 0, 0? Would that work? So some of these work and some of them don't. Okay, so just because you have two vectors doesn't always mean that you're spanning R2. Some of those will work and some of them won't. I can't help it. There's like so much that I want to talk about in regard to this statement. I want to ask you, do you think it's possible to come up with a single vector instead of a pair? Do you think we could come up with a single vector that's the span of a single vector equals R2? What would that vector have to be? Could it be 1, 0? Could it be 1, 1? Or do you think, no, it's impossible for that to work with only one vector? You're not going to get the linear combination you need. I'm going to leave that as kind of an open question. I'm not going to answer that yet. We're going to be answering those sorts of questions in the course. Okay, for now, instead of getting ahead of myself and thinking about future sections, let's see what does this have to do with systems and solutions to systems. Earlier we had Theorem 3, and now we have Theorem 4. Theorem 4 says, let A be an M by N matrix. Then the following are equivalent. We're going to have 4 statements here. We're going to write 4 statements that we are saying are equivalent statements. What that means is that either all 4 of them are true or all 4 of them are false for a given matrix A. Okay? First statement. For every B in Rm, AX equals B has a solution. Okay, this theorem right now, it doesn't really mean anything yet until I start writing subsequent statements. We're going to say some other statements that are equivalent to that first one. Second statement. For every B in Rm, B is a linear combination of the columns of A. Okay, so that is sort of bringing in something that we said earlier. I think I said that earlier as a fact. I think I even said that that looked like it could have been a corollary to Theorem 3. I wrote it as a fact after Theorem 3. We're incorporating it into this thing called Theorem 4. So these two statements so far, there's going to be a total of 4 of them, but these two statements so far are equivalent. If I give you a matrix A, then either both of these are true or both of these are false. Depends on the matrix A. You can't have one of each, though. You can't have one of these things true and one of them false. All right. Next thing, the columns of A span Rm. Okay. Columns of A span Rm. We've started to do some little examples of, sets of vectors that span R2. We've seen some sets of vectors that span R2. All right, I said there were going to be 4 of these. This one is more about the actual row reduction that you would do to solve a system. And it says A has a pivot position in every row. Interesting. Interesting. Okay. So where's the proof of this? Here's what I want to say about this theorem. Statements A, B, and C are equivalent to each other by our definitions and our discussion so far in this section. That takes care of the equivalence of A, B, and C. For the equivalence of statement D, well, there is a proof in the recommended textbook. So I'm not planning to do it here in this lesson just for the sake of time, but it does wind up being equivalent to these. So let me repeat. When I say the following are equivalent, we're given a matrix and then the following are equivalent. This means that either all 4 of these are true or all 4 of these are false. For a given matrix A, these could all be true. And for some other matrix A, these could all be false. But you're never going to get a mix and match of some of them true, some of them false. Okay? Example. Statements A through D are all true when A equals this matrix. All right, would you like me to prove that to you? We already have. How about that? We already have. Now I'm going to say, because we proved C earlier. Check it out. I can move the page a little bit. Maybe I'll show this at the top of the screen. Bam, right there at the top of the screen. That's the claim. The claim was that the span of these two vectors equals R2. right? We did prove that. So, for this given matrix A, we have already proved that the columns of A span R2. And because statement C has been shown to be true by theorem 4, the rest of them have to also be true. Pretty cool. I think you could also look at this matrix, and I think that you could see that it has a pivot position in every row. There's 2 rows, and I think you could show that there's 2 pivots. So then you'd be showing statement D, and then you'd be able to conclude that the rest of them are true. But you don't have to prove all 4. Just prove one of them, and then the rest have to follow. Okay, so that was theorem 4, and theorem 4 is important. We are going to refer to this in future sections. I'm going to put maybe a star next to it, or maybe you could highlight it or something. Not to say that the other theorems are less important, but I think that this is one that we are going to come back to. Right now, I have theorem 5 to tell you about. I think theorem 5 we're going to prove. We'll go through it. Let A be an m by n matrix. Let U be a vector that lives in Rn. V is a vector from Rn. And let C be a scalar. What does scalar mean? It just means C is a real number. We could have just said C is from the set of real numbers. All right, then this theorem has 2 parts. First one says A times U plus V is equal to AU plus AV. This is just about matrix times vector arithmetic. Next one says A times CU equals C times AU. Now, we had a list of properties, I think, in one of the previous lessons about properties of vectors and matrices and stuff. And these are some properties that we can add to that, I guess. We're saying that a matrix times vector multiplication, which we didn't really define until the beginning of this lesson, it does distribute across parentheses the way that you would expect it to. You would kind of expect the A to distribute across parentheses. This theorem says it does. What is part B doing? Part B is a little bit weird. It says C is a real number. So this is when you have a matrix, a real number, and a vector all in the same problem. And it's saying that you can pull the real number out front. And I would kind of expect that. I would expect that, real numbers can usually be pulled out of things. So I think what we're going to do is I'm going to prove part A, and then I'm going to ask you to try to prove part B. All right, so maybe my proof of part A will help you get a sense of how to work with these types of proofs, and then you'll be able to do part B. All right, I want to start by saying let A be made up of these columns. Where A1, A2, etc., up to AN are all in Rm. The reason I'm doing that is because the way that we discussed a matrix times a vector at the beginning of this lesson was based on writing A in this way. I'm then going to say let U, U is supposed to be in Rn, but I would like to explicitly say what the entries are called. I'm going to call them U1 up to UN. going to say that V is composed of V1 to Vn. By the way, don't put vector symbols on things unless they are a vector. So like the U1 through UN, those are just real numbers. V1 through Vn, those are just real numbers. But V needs a vector symbol above it. U needs a vector symbol above it. And C is in the set of real numbers. All right, all of this at the beginning of the proof was to kind of establish all the pieces of the puzzle, all the pieces that we're going to be working with. Now, we would like to show this statement, which I'm going to be moving off the screen in a moment, but we want to show this equals this. Left-hand side is some expression. Right-hand side is some expression. These are not sets. It's not like the proof we did earlier where we had a set equal to a set. No, this is just an expression equals an expression. So to show that the left-hand side equals the right-hand side, we just start with one of the sides, do some algebra or whatever we need to do. Let's start with the left-hand side. We're going to start with the left-hand side. We're going to show that it equals the right-hand side. Okay, so here is the left-hand side. You could probably start with either side and make this work. I would like to write this in terms of, at the beginning of this lesson, we defined what it means to have a matrix times a vector. So A1 up through AN is getting multiplied by parentheses. Let's write out all these entries. U1 up to UN plus V1 up to Vn. Okay, looks good so far, right? We'll have a chain of equal signs. This equals this, equals that, equals that, equals that. And eventually we'll show that it equals the right-hand side that we're trying to prove. I think what we should do here is simplify the part in parentheses. It's a vector plus a vector. So really, we could just write it as a single vector. Maybe like that. So now I have the matrix A written as all of its columns, and it's being multiplied times a vector. How do we do a matrix times a vector? Well, at the beginning of this lesson, we said you take the first entry of the vector times the first column of the matrix plus the next entry of the vector times the next column of the matrix, and so on, until you get to the end, and you should have the number of them line up. UN plus Vn times AN. Yes, it does line up. Maybe at this point, now is a good time to take a step back and remind ourselves, what is it that we are trying to prove? I moved it away. We moved it off the screen. Let's take a second look at it. Get it back just for a minute here. This is what we're trying to prove. We started with the left-hand side. We're trying to show that it equals that. From where we're at right now, I'll point to both things. From where we're at right now, can you see how are we going to get from where we are to what we're trying to show? What we're trying to show is A times a vector plus A times a vector. I think we can make this work. I think we can make this happen, right? Here's what I'm going to do. Let's, distribute all these parentheses here. Let's say U1 A1 plus V1 A1 plus U2 A2 plus V2 A2 plus ... UN AN plus VN AN. Okay? Now, here's a crucial step. We have a lot of terms here, right? Let's group together. In fact, I'm going to put big parentheses here. I know what I have in mind. I want to group together all of the things that involve u's over here and all the things that involve v's over here. Why am I doing that? Because look up here. We want a times u plus a times v. I have my plus symbol. That's the plus that goes here. That's the plus sign. All right, I want everything involving u here, so we can do it. u1, a1, plus u2, a2, etc., up to un, an, and then in the other one, we'll put everything involving v. v, n, a, n. And we did this because what does this whole thing in parentheses equal? It equals AU. And what does this other thing in parentheses equal? It equals AV. So we're done. We started with the left-hand side. We did the definitions. All we did really was work with definitions. I think there was one step here where we used a property from an earlier lesson that was on I think it was probably on a big list of properties about vectors. But right here, we used the fact that you can distribute the u1 plus v1 parentheses. You can distribute that times this vector. Other than that, it was just like the definition of matrix vector multiplication. And we're done. Left-hand side equals right-hand side. I'm going to put a little square to say that we're done with the proof. That's really just the proof of part A. So I was suggesting that I would like you to try to prove part B. So how can I do this? I'll have part B on the screen a little bit. And I'm going to ask you to try the proof of B. All right, so what I'd like you to do, this is what we're trying to prove right up here. I'd like you to maybe pause the video, spend a minute or 2 or 3 or 4, and see if you can write a proof of that part of this, proof of part B. Once you've paused the video and spent some time on it, you'll come back and I'm ready to talk about it. So hopefully you tried that. I'm going to move the top page away. I think everybody has the statement of Theorem 5 in their notes. All right, so I'll show you how I approached this. First, I started this in a very similar way. I said let A equal this, where A1, A2, etc. are all in Rm. I said let U equal U1 through Un. That way, later in the proof, if I need to refer to the entries of U, I've given them a name. And if I say something like U1, U2, U3, it's not a mystery what I'm talking about. I'm talking about entries of U. And C is a real number. Okay. I think that this one might actually be easier than part A because part A had a U and a V. We have, let's see, can we show that the left-hand side equals the right-hand side? So A times CU. Let's rewrite this as A being composed of these columns, because that has been helpful to us so far. And in parentheses here, let's write U as U1 up to UN. Here's a question for you. Can we take C and just pull it all the way out front? Like right now, can I just take that C and move it out front? Well, no, not really. Because if I just took that C and moved it out front, I would be using Theorem 5 Part B to try to prove Theorem 5 Part B. You can't do that. You can't use that just because it looks like it's probably true. You can't use a theorem to prove itself. We need to get every little detail in here. And then once we've proved it, then from then on, it'll be okay to use it. I think what we could do is get this thing in parentheses to just be a column vector. Like bring the C inside that vector. So CU1 to CU. This looks like a matrix times a vector. We talked about the definition of a matrix times a vector at the beginning of this lesson. You take the first entry of the vector times the first column of the matrix plus the next entry of the vector times the next column of the matrix. Keep going until you get all the way to the bottom of the vector, and you're taking the last entry of the vector and the last column of the matrix. You see how the C's kind of moved themselves out front anyway? They kind of just naturally wound up, the C's all kind of wound up on the left. That's good. Now it would be okay, since C is a real number, it would be okay for me to pull C out of this. I could factor a C out of this. Remember here that C is a real number, U1 is a real number, A1 is a vector. Like, remember which things are numbers and which are vectors, but it is okay to factor out a C now. So it kind of wound up moving itself to the left side of things anyway. And this equals C times AU. And that's exactly what we were trying to prove. So we'll put a little box here to say that's the end of the proof. Little box or a little symbol or something. So it was really the definition from the beginning of this lesson, the definition about the product of a matrix times a vector, that got us from this line to the next line. That was really the important part. And then I guess when I factored out the C, I was using, that's probably a property from that list of properties of, you know, scalars times vectors from the previous section. All right, so we are wrapping up our lesson on the matrix equation AX equals B. This I think was kind of a tough section. It covers a lot of abstract stuff, and you know, it had more theorems than we've seen in some previous lessons. But it's a pretty important section. I think we're going to come back to some of these topics throughout the course. I'll tell you that the next video lesson that you see from me is going to just get back to talking about solutions to linear systems. Now, we can't just solve systems all semester. There's you know, we solved systems on the first day of the class, and there's more to linear algebra than just doing that. But what we're going to do in the next video is talk about solution sets to systems. In particular, we're going to talk about the case where there's infinitely many solutions, because that needs some discussion. Okay, so that's it for right now, and hope everybody is doing well, and I'll see you next time.